Hi, I'm Alistair, and in this video I'll be comparing different ways to make things move. I don't mean vehicles, but linear mechanisms that make props rise and fall in escape rooms, haunted houses, theatrical effects, things like that. Now, the easiest way to make an item move is just to rely on the force of gravity. So here I've got a catch, and if I pull that across, I can use it to secure an item like this block of wood, suspend it somewhere high up, and when I release the catch it will fall to the ground. And if you add a hinge on the other side of the catch, that's how you make a trapdoor. And simply releasing a catch to let something fall is how effects like drop windows, trapdoors, or kabuki drops in theatre are achieved. Now, of course, gravity only works in one direction, which is downwards. If you want something that rises up, you could instead use a gas strut. Now, these are the same things that make your car boot lift up. So you compress them to store up potential energy, and then when you release them, they expand again. And these can apply a lot of force. They're good to make things like heavy chest lids open or pedestals rise up. They're very simple. You just force them shut, and then you need to use a catch or a maglock or some other weight to hold them there. And then when you release that catch, they expand again. But as with the gravity-based mechanisms, these are one-time only uses. You can remotely release a catch that makes a trapdoor fall open or a gas strut to rise, but after that they're going to need to be manually reset before they can be used again. Now, if you want something that can be automated to move up and down, you might consider an electric linear actuator. Now, these use an electric motor, a gear train and a lead screw that converts the rotary motion of the motor spinning into the linear motion of the shaft extending. Now, there's a lot to like about linear actuators. They're pretty easy to wire, they generally run on 12 volts DC, and you just reverse the polarity of the power supply to make them expand or contract. Now, they've got built-in limit switches, so you don't need to worry about them burning out, and you can always disconnect power at any point to make them stop mid-travel. But there's also a few limitations. The biggest problem, as you can probably tell, is that they're very slow, typically only moving at about a centimetre a second, and you can't really do anything to adjust that speed. The second problem is that they can be a bit fragile. If their movement gets blocked, but you continue to try to extend them, the gears will grind and you can end up stripping the teeth of the cogs or overheating the motor. And unfortunately, that fragility is made worse by their slow speed. If you use an actuator like this in an escape room for a reveal, players sometimes get impatient and try to force them open, and if that happens repeatedly, they can be damaged. And that brings me neatly onto another alternative, which is pneumatic cylinders. So, like gas struts, these use the force of compressed gas to move the piston, and that gas is usually just air. However, unlike sealed gas struts, which contain a fixed amount of pressurised gas in a closed system, a pneumatic cylinder has ports at either end that you can hook up to an external air source. Now, if the pressure of air supplied at the base is higher than the pressure of air at the top port, the rod extends. While if the pressure at the top is higher than the pressure at the bottom, then it contracts again. So this cylinder is a very simple, purely mechanical construction. It doesn't have any gears or motors or electronic circuitry, and that makes it really durable and reliable, which is why pneumatics are still commonly used in industrial scenarios. And it also fixes many of the problems I just described with the electronic linear actuators. Firstly, pneumatics are fast, really fast. Their speed is really only limited by the pressure of the gas you supply, and even a very modest air compressor can generate a huge force when directed into a cylinder like this. Also, unlike electric linear actuators, you can adjust that force. So by adding adjustable valves, you can regulate the pressure in different sections of pipework to make the cylinder expand and contract at different rates. And that gives you a different quality of motion compared to an electric motor.
It's almost like comparing an analog value and a digital value. Because gases are compressible, the piston is always a bit springy. I can manually push it down and it will contract a little more. It's just increasing the pressure on the other side of the piston in the cylinder, so that when I let go, the opposing force just makes it return to its equilibrium point, and there's no risk of a motor stalling or grinding any cogs. And you can control pneumatics with push buttons and switches or solenoid valves triggered by relay, much like an electronic system. So you can program a sequence of motions that are executed by an Arduino or show control software, and that's often how animatronic displays are automated. Now, there are some downsides to pneumatic systems. Firstly, they lack fine control. You can't really stop a pneumatic cylinder part way. They're either fully contracted or fully extended. And although you can adjust the pressure to change the speed of that movement, it's very hard to precisely fine-tune that. So if you wanted a motion that lasted exactly 2 seconds, say, that would be very difficult to guarantee compared to the fairly predictable rate of movement of a linear actuator. There's also some work and cost involved in first setting up a pneumatic system. You need a source of compressed air and the pipework that then takes it to your prop. Air compressors can be a bit noisy, so you might want to locate that somewhere a short distance away, and then you'll have to run tubing to it. Now, pneumatic tubing's pretty cheap, but it's something else that you'll need to install and maintain. Now, fortunately, once you have got that installed, it's then very easy and cheap to add additional cylinders. And it's very clean, and if you're only operating at low pressure, as I am, it's very safe too. So that's just a brief summary of some of the different methods you can use for generating linear movement, each with their own advantages and disadvantages. I hope you found it useful. I myself am involved in a project at the moment that's using a lot of pneumatics, and that's something I've not done a whole lot of before, so I've really enjoyed learning more about it myself, and I might go into more detail about that in an upcoming video. Otherwise, if you've got any questions, comments or tips about any of the methods used in this video, or perhaps you've got a completely different approach to generating movement, please do leave a comment below. I'd love to hear about what you've been up to. Otherwise, I just want to say thanks very much for watching, and I look forward to seeing you next time. Okay, cheers, bye.